Hello everyone. Today we are going to discuss a special topic, that is plastic analysis. So you know about the basic things of plastic analysis. So what is plastic analysis? Why it is required in GATE, and what is the real life problem? Today we will go in the basic discussions of the basic things of plastic analysis, like the introduction, what is plastic analysis, like what is plastic analysis, why it is important, for GATE and for real life problems. So this is the basic introduction. Now then we will discuss the basic thing about shape factor. You know shape factor? There is some shape factors in civil engineering, like in plastic analysis a shape factor, in geotechnical engineering that portion terrace analysis, that is also a shape factor, and permeability chapter, you know that number of flow lines, number of equipotential drops, so that is also a shape factor. So here we will discuss the shape factor of plastic analysis. What is the shape factor of different types of shapes? So then we will discuss some procedures. What is the procedures? For any analysis there should be some procedures. Like here we can go by any theorem, like static procedure or static theorem, or we can also go by kinematic theorem. So this is the procedures. Then we will show you some examples, few illustrative examples. And then we will show you that some GATE problems. So 2 to 3 GATE problems. So this is our basic discussions of plastic analysis. So now first is, what is plastic analysis? You know that still now in any of our design problems, in most of the design cases, we know that is basic stress strain diagram like this, right? Also you know that this is a figure of stress strain diagram for steel, right? We know this. Now up to a certain limit, like this portion, we can guess that this is in the elastic zone. So what is elastic zone? What is elastic zone or elastic analysis? What is elastic zone or elastic analysis? In some portions, suppose if I applied a force or a pressure on a body up to a certain limit, then after that body, after when the load is taken back, then the body gets to its initial positions. That is elastic analysis. Like suppose if we take a simple stress strain diagram of a steel member, then we can see that up to this is the elastic limit, but after that portion, some portion, that is plastic limit. You know this plastic limit, then a breaking point will come. So this is the basic thing of plastic analysis. Generally we have discussed about elastic problems, elastic materials which obeys Hooke's law, and we have discussed up to here. But in plastic limit we will discuss the further. So that is the basic difference between elastic analysis and plastic analysis, right? So now this is the basic introduction of plastic analysis and compared to elastic analysis. Now let us move to our second thing is shape factor. Now the question is, what is shape factor, right? We know the basic thing like, before that, why it is important? You know that? Why? In some prospect of GATE and some real life problems, if you see the previous year's GATE question papers, you can see that every year, almost every year, a 2 marks question have come from this topic, plastic analysis. You can see this. Every year, almost every year. Last year, it means GATE 2017, this portion, this question, there is not a single question from this topic. So you can expect at least 1 mark, one question from this plastic analysis this year GATE 2018. And what are the real life problems? You know, everything. In steel design, in steel structure design, main analysis or main procedure of how much moment can it be taken, it's done by only plastic analysis. Suppose in a frame, in a steel frame like this, the maximum moment carrying capacity of the beams of the frames of the whole frame can be done by only plastic analysis for the steel frames, right? So this is our real life problems. So this is the basic introduction of plastic analysis and the difference between plastic analysis and elastic analysis. Now let us move to shape factor. What is shape factor? Shape factor is denoted as S, that is equal to plastic modulus by elastic modulus, right? Where ZP equal to plastic section modulus and ZD equal to elastic section modulus, right? This is the term as shape factor, right? And you know this term, elastic section modulus, right? Let us take a simple, our known example. So for shape factor, take an example like this. If we consider a rectangular beam like this, this is a rectangular beam, then we can get elastic section modulus equal to I by Y. So it will come BD square by 6, right? You know this. I equal to BD cube by 12 by Y means D by 2, right? It will come BD square by 6 for elastic section modulus. Now, the question is for plastic section modulus. It will be what? The area, total area by 2 into Y1 plus Y2. Right? So, what is the area? You know B into D, total area, by 2. Right? Now, what is Y1? Just take a neutral axis. This is neutral axis. This one. And Y1 is the distance of the centroid of the upper portion. So, it will come again some value, and Y2 similarly some value will come. So it will be D by 4 plus D by 4, right? So then it will come BD by 2 into D by 2. So hence BD square by 4. So this is our plastic section modulus. Hence shape factor is equal to ZP by ZE. BD squared by 4 by BD squared by 6. So it will come 1.5. Right? So this is a shape factor, or this is a basic example how to calculate the shape factor for different types of sections. So this is I have shown you for for a basic example of shape factor of a rectangular section. Please mind it, this is for a rectangular section. Right? Now let us take some standard cases for shape factors. Standard cases means like different types of sections. So for rectangular section, let us give number 1, rectangular section, shape factor has come 1.5. Number 2, triangular section. Triangular section. Now please mind it, for triangular section, if the shape is given like this, and this is the height, right? This is a triangular section like this. If this type is given, then shape factor equal to 2.34, right? And if the triangle is given like this is a neutral axis like that, then shape factor will be 2.0. Got it? So this is a basic difference of a triangular section. Now there is another things like I section. For I section, you can go through your IS codes, IS 800, IS 800 2007. You can find that for I sections, shape factors are different. So, but there is a certain range of the shape factors, that is 1.1 to 1.2. Like this. You can also find this in your IS 800 2007. Number 4 is circular section. For circular section, it will be simply S equal to 1.7, like this. Now, hollow circular section, it will be 4 by pi. For hollow circular section, like this. And then last one is diamond section. Diamond section, shape factor will be simply 2. All the things, all the calculations of shape factor can be done by simple this formula, plastic section modulus by elastic section modulus. And this is all our standard cases. These all our standard cases are really important for GATE. In a single marks question or 2 marks questions, there will be some options given regarding this, and you have to find the matching things regarding these shape factors. That's why shape factor is really important. Right? So this is the basic things of plastic analysis. That is the introduction, difference between plastic analysis and elastic analysis. Then why shape factor? What is shape factor? That is also related to plastic analysis, because we are considering plastic section modulus. Now we will procedure to the different type of procedure to find the plastic analysis or find the collapse load, like that. So let us discuss some procedures. What are the procedures? What are the procedures of plastic analysis? Procedures, you know, static theorem and next one is kinematic theorem. So you can discuss or you can find the plastic analysis by static theorem as well as by kinematic theorem. What is static theorem? Static theorem says that, or it will deal with higher safety factor for analysis of plastic analysis. Static analysis, it deals with higher safety factor. Higher safety factor. That's why its other name is upper bound theorem. Right? Upper bound theorem. This is one of the most important thing again, static theorem. It can be also known as upper bound theorem. And for kinematic indeterminacy, generally we have considered for kinematic theorem lower safety factor. And that's why it is termed as upper bound theorem. Because in kinematic theorem, we generally go with the ultimate load value. Ultimate load value means lower safety. That's why it's termed as upper bound theorem, maximum load. So this is the basic thing of a static theorem, and this is a thing of kinematic theorem. Now, what is the design procedure for static theorem? Just imagine this is a propped cantilever. We have to find the collapse load here. Just imagine. First step is step 1. We have to make it a determinate structure. Make it determinate structure. Right? Determinate structure. You can make the determinate structure by 2 ways here. Right? Just here you can make the fixed end as a hinged portion, or you can also make the structure in this portion by removing this redundant. So you can also make like this one or this one. This is a statically determinate structure. Then draw the bending moment diagram of this indeterminate structure. After that, bending moment diagram with the redundants. Then combined bending moment diagram. Right? Like this way you can find the plastic analysis collapse load in this procedure, that is static analysis. This is the basic procedure. But in kinematic theorem compared to static theorem, this is easier, and actually all of the problems in your gate examination should be solved by this way. Why? Because this is the easiest way and this is the quickest way. This is the main reason, quickest way. So what are the basic thing? Internal work done by external work. Simple. That is the energy method. Internal work equals to external work. Internal work equal to external work. This is the theorem which is useful to solve by kinematic theorem and plastic analysis. Only this theorem will help you to solve this one. Right? So I hope you got the basic things up to now. Elastic analysis and plastic analysis difference. What are the difference between elastic analysis and plastic analysis? Then what is the shape factor? Why shape factor is required here? You know that because it is already related to plastic moment capacity as well as plastic section modulus, shape factor. Now procedures. We can solve the examples, any examples of plastic analysis by 2 procedures. That is static theorem and another is kinematic theorem. This one. Procedures. So by procedures, we should go by only kinematic theorem. Why kinematic theorem? Because it is the easiest way and it is the quickest way. Right? So this is the procedures. Now, how to find the collapse load of plastic analysis. Now we will show some illustrative examples, right? Let us discuss few examples, then I think it will be clear for you. Few illustrative examples by kinematic theorem to find the collapse load in plastic analysis. It will clear your doubts. So let us try to solve. Before kinematic theorem and before solving few illustrative examples, let us go the procedures. We know that for kinematic theorem, external work will be equal to internal work, right? Now external work, we know that load, for point load it will be simply, P into delta, right? And for UDL it is half into P into delta in general, right? For UDL, this is the point load for external work. Now for right side portion, what is internal work? What is internal work and how it can be calculated regarding plastic analysis? So for plastic analysis, we have to find the collapse load. We have to take care of plastic moment capacity, right? So regarding plastic moment capacity or regarding internal work done, let us discuss again few, like we have to find first step one, that is finding plastic hinge locations. Right? So where the plastic hinge locations will come? So plastic hinge locations, step 1 or case 1. Suppose this is a fixed beam. Then plastic hinge will come here and here. So number 1 is for fixed beam, plastic hinge will come at the fixed supports. This is number 1, fixed supports or fixed ends. Number 2 is point load acting. Suppose, again consider the same structure like this one. A point load P is acting, then plastic hinge will come here. Another plastic hinge will come here. So at the point loads. So this is our case 2. Number 3 is take the same. Now, take the same. Till now we have discussed only point load. This point load can be anywhere in the beam. This side, middle portion, anywhere. So that portion, a plastic hinge will form. But suppose the whole structure, the whole beam is subjected to UDL. Then a point load will come at the zero shear. What does it mean by zero shear? At zero shear. What does it mean? Zero shear means only one thing, maximum bending moment. For this beam, for this fixed beam, suppose maximum bending moment is acting or is occurring at the mid support or in the mid portion in the whole fixed beam. Now for the mid portion, maximum bending moment will occur. So maximum bending moment where occurs, there will be occur zero shear. So there a plastic hinge will form. So these are the plastic hinge locations. Fixed supports under the point load and where there is zero shear. Right? Now take case 4. Suppose there is sudden change in the geometry. Like this. So a plastic hinge will occur here where the geometry changes. Suppose this portion moment carrying capacity, or this portion has flexural rigidity EI and this portion has 2 EI. Now this is for elastic analysis, right? This is for EI, 2 EI, we have seen this, but these things are for elastic analysis, right? Here we're considering plastic analysis. So just imagine this is small mp and this is 2 mp. So different geometry, same member with different moment carrying capacity. Now the section changes here. So where the geometry changes, in this portion a plastic hinge will form, right? And similarly here will plastic hinge will remain like this. So this is our case 4. There is another case that is for continuous beam. What is that? Suppose, just imagine, there is a continuous beam like this. Right? So in continuous beam, where two members, this is member 1, this is member 2. Two members are meeting at a portion, there a plastic hinge will form. So these are the cases where we have to find or we have to locate the plastic hinges and have to carry forward our calculation of plastic analysis by kinematic theorem or kinematic theorem. So this is the basic things of plastic analysis and procedures, how to go forward for solving or for finding any collapse load of plastic analysis by kinematic theorem. Right? Now let us discuss few examples. Okay, so just taking a simple problem and finding it and find the collapse load by plastic analysis. Just take a simple problem. Suppose this is example 1, like this thing, at middle point, load P is acting, right? And the length is given as L. Total length, just assume this is total length equal to L. And plastic moment is given as MP in the whole section. This is same geometry. So let us consider the plastic moment is MP in the whole section. Find the collapse load. So this is our job and this is our task. Find the collapse load. You can go through our previous year's questions in GATE examination. Simple questions like this have been asked. Simple question like this. Example 1. It can be itself a GATE questions. Right? This one. Now let us solve the plastic analysis, this one, or finding the collapse load P in during plastic analysis or by plastic analysis by kinematic theorem. So, kinematic theorem, we all know this, external work equal to internal work. This is the basic things of kinematic theorem, right? Now, our first task is draw the plastic analysis diagram. When the beam is like this, right? After loading, the beam will be like this one, right? This one. So it will create an angle theta. It will create an angle theta here, right? So again theta, right? Due to symmetry, this length and this length, this length and this length are same. You can see that middle point load is acting, this length and this length are same. So simple, again same theta, right? So theta, just increase this portion, it will again come theta. So total here, it has come, here total has come to theta. Like this, 2 theta. So, where the plastic hinges will form? One plastic hinge here, this is a fixed portion. One plastic hinge here, this is also a fixed portion. And one plastic hinge here, this is also a concentrated load is acting. So 3 plastic hinges, 1, 2, 3, 3 numbers of plastic hinges, right? 1, 2 and 3, 3 plastic hinges. Hence, we can write internal work, right? MP, that is given MP into theta, this angle theta, plus MP here theta plus theta, right? And here a plastic hinge will form, so MP into theta. So this is the way you can find the internal work in plastic analysis. First job, where to find the plastic hinge locations? Here, here and here. So here, here and here, right? Just we find this. So it will come 4 MP theta. Right? Now, again, external work. What is external work? Load into deflection. What is load? That is P into deflection. This deflection is, assume this is equal to delta. So this is equal to delta, right? Delta. So P into delta means, what is delta? Just take this triangle, small triangle, right? This is delta and this is equal to L by 2. This portion. Just take this triangle here. So from here you can find tan theta equal to delta by L by 2. Now theta is very small in real life. Theta is very small in real life problems. Theta is very small angle. So we can calculate or we can write theta equal to delta by L by 2. Like this. Hence, we also can write delta equal to theta into L by 2. So this is our external work and this is our internal work. Now just, we know this external work equal to internal work. You can simply find it now. So, after finding or after solving external work equal to internal work, we can simply write from this 4 MP, P into theta into L by 2 equal to 4 MP theta. So P equal to simple 8 MP by L. This is the collapse load by plastic analysis. This is the collapse load you have to find in your examination by plastic analysis and by kinematic theorem. You can find this is very easy by kinematic theorem, right? No issues. Only you have to find the plastic hinge locations. You have to give a load. You have to find the internal work. You have to find the external work. Just make it equal. You will get the collapse load. Simple things and 2 marks question. Now this is a simple problem for a fixed beam. You can see both the ends are fixed. So this is a fixed beam. Now just go another example. Example 2 like this. Example 2. This example. Now just make it, this portion is a roller. This portion is a roller. Only simple change. I have made this side fixed portion as a roller. Now find the collapse load. Now we have to find the collapse load. So simple, again draw the diagram like this. Like this. This will be the total deflection delta, like this one. This is angle theta. Angle theta, due to symmetry, simple same angle will come theta, and this angle will come theta plus theta, right? So internal work, what is internal work? A plastic hinge has come here. A plastic hinge has come here. There is no plastic hinge. Please go through the plastic hinge locations. You can find that there is no plastic hinge will form in the roller supports until it is a continuous beam. Until it is a continuous beam. Right? So plastic hinge at the fixed end portion, plastic hinge at the point where point load or where concentrated load is acting here, but this case, example 2, there is no plastic hinge like previous case because the fixed portion has been converted to a roller portion, so no plastic hinge. So this is the basic difference. Else everything is same. Like external work, this portion MP into theta, this angle plus this portion MP into theta plus theta. So simple 3 MP theta. Right? And external work, what is external work? Just P into delta. So again you have to find the delta, and this is equal to L by 2, and this is theta. So we can write tan theta equal to delta by L by 2, right? So theta is very small. In real life problems, these problems, theta is very small, angle is very small. So we can write theta equal to delta by L by 2. Just write delta equals to theta into L by 2. Right? So simple P into theta into L by 2. So simple, make it external work equal to internal work. We can write P into theta into L by 2 equal to 3 MP theta. Just make theta cancel. It will come collapse load P equal to 6 MP by L. Right? So this is the basic difference if the fixed portion is converted to roller. 6 MP by L. Right? Simple. Only one change, and there is some change, and there is some less value in collapse load. So this is the basic things. This is the basic things of plastic analysis. And now again, just assume this portion, example 3, like this, and I have converted this fixed end portions also as a hinged one. So this is converted as a simply supported beam. This is simply supported beam. We are converting the fixed beam first prop cantilever, then a simply supported beam. Now again same conditions, we have to find this one, collapse load. So for this simply supported beam, just we are converting this fixed portion into a hinge portion. For hinge portion, there will be, please remember, for hinge portion, there will be no plastic hinge locations here. So just remove these plastic hinge locations. No plastic hinge. Rest, it will remain same. There will be no plastic hinge. So this side, no plastic hinges. Right? Hence, internal work done. This will be erased. So it will come only 2 theta. Like this. And external work, it will remain same. So it will come only 4 MP by L. So you can see that. That fixed beam is converted to prop cantilever. Right? Then collapse load is reduces. Why? Because suppose this is a fixed beam like this, and I am applying a point load P here, right? In this case, a moment will come and it will try to resist some amount of load. Now, I am giving it as a roller one. Here, there is no moment, or the moment is 0, so only this one. That's why the collapse load P has reduced. This case, again I am reducing this one. So there is no moment there is no moment in these cases, only beam has to take the whole load, right? So that's why it has again further reduced from 8 MP by L for fixed beam, it has reduced to 4 MP by L to a simply supported beam with 6 MP by L in a prop cantilever. So that's the case of plastic analysis. Very simple and very interesting, right? So this is the cases of illustrative examples like this one for plastic analysis. Now there is few other examples considering different types of beams or different types of support conditions like continuous beam with some point loads and if certain geometry changes, suppose that is also a problem. Also some problem like whole portion is acting as a UDL. There will be some geoshear span, you have to find the collapse route like this. So these are the cases or these are the illustrative examples can be solved by plastic analysis. Now let us discuss a previous year's gate problem. So this will be easier for you. This will be very easier for you. Just take a gate problem. Right? The problem is a simply supported overhanging beam. A simply supported overhanging beam. Right? We are providing a load P here, downward direction, and we are providing a load at the overhang portion P by 2 here. The whole portion, moment capacity, plastic moment capacity is MP. This is the given problem. The whole portion, plastic moment capacity is equal to MP. So what will be the collapse load? Collapse load P will be what? Simple problem. Like we can see this, like previous problems. So let us try to solve. So our first task, finding the deflected diagram. So finding our deflected diagram. It is our first objective. Like this. Now, point load, middle point, this load is more value. This point load has more value than this. So it will try to deflect in the downward direction like this. Up to now, there is no doubt, right? After deflecting the real beam into the deflected shape, just imagine this is a deflected shape. This is the deflected shape of the beam. This one. Now what will we do to the other portion? This one. It will go upwards like this. It will go upwards like this one. Just we are providing a load P in this downward direction in the beam. It will be deflected like this and a plastic hinge will form here. Right? There is a formation of plastic hinge in the middle point. A load is given like this. Take this length L by 2 and this length is L by 3. This length. Plastic hinge has formed here. So deflected shape should be like this for this portion. Right? Now, if this portion is deflected like this, then the overhang portion has to go upward direction like this one, this side. This is a simple case. Simple. Just try to think this simple way. What will be the deflected shape when there is a hinge? Right? You have gone through the influence line diagram, deflected shapes. So here, I think you also can take the concepts of the deflected shape. Now take that. This is delta. Total deflection here. And take this is equal to delta 1. Why different? Because load is also different. So we can expect there should be some different external energy. Because load is different. So different external energy. Now please write. External energy will be what? P into delta minus, because it has gone upwards and it is downwards. Right? it is downwards. So that's why it is plus P into delta. This is gone upwards. That's why minus P by 2. Here the load is P by 2 into delta. Now please find the what is delta. You can also find out. This is theta, this is delta. So we can write tan theta for first case, this side equal to L by 2, tan theta equal to delta by L by 2, right? So delta equals to theta into L by 2, write this. So we can write P into theta into L by 2 minus P by 2 into, this is delta 1, this is delta 1. So what is delta 1? Simple case, only this side, this triangle, like this one. And only difference is the length is L by 3 instead of L by 2. So we can write theta into L by 3. So this is our external work done by the beam, right? Now find the internal work done. What is internal work done? There is no plastic hinge because this is a simply supported beam of a hinged portion. No plastic hinge. Point load, plastic hinge. This portion, no plastic hinge. Right? Now there is only one tricky question here. Sir, this is a point load is acting, but why sir there is no plastic hinge? This is the only tricky one. So only tricky one is like that. This is a cantilever portion like this side, right? We are providing a load at a free end. But in this case, there will be a deflection like this. But there will be no plastic hinge formation here. The question is why? Because if there is plastic hinge formation in this portion, there should be some remaining portion of the member this side. What does it mean? What do we mean by plastic hinge? Just take a simple member. A hinge has created. If I apply a load here, it will deflect like this. It is a deflected shape. It is not a plastic hinge shape. This is the only tricky one in the whole plastic hinge analysis. If load is acted in a cantilever beam and in the free end portion or any portion in the free end portion here, then there will be no plastic hinge. There will be some deflected shape here, but no plastic hinge will form here. Only plastic hinge will form here. So this is the trickiest question in all the plastic hinge cases for point load. So hence we can write that internal work equal to, what is internal work? Only this portion. So this portion has MP into same angle. This is theta. This is the opposite angle, right? So theta. Only opposite angle. It is overhang portion. This is the overhang portion, right? Overhang portion. So same angle will act like this, theta. And due to symmetry, it will come theta plus theta. So 2 into MP into theta. Now just make external work equal to internal work. So we can write P into theta into L by 2 minus P by 2 into theta into L by 3 equal to 2 MP theta. Now please try to solve. The theta will be cancelled. Theta will be cancelled like this. Theta will be cancelled. So we can just write down P equal to how much? 6 MP by L. So this is the collapse load for our desired question. What will be the collapse load? P equal to 6 MP by L. This is one gate question has come in few years ago. These gate questions. So this is whole basic plastic analysis. The introduction, basic things. What is the difference of plastic analysis and elastic analysis? Now what is shape factor? Why it is important? What is related to shape factor? why it is related to safe plastic analysis, that is also discussed. What are the procedures to find the plastic analysis problems? Two procedures, you know, static theorem and kinematic theorem. And in these cases, we have gone only by kinematic theorem. Second one, kinematic theorem. We have shown also illustrative examples. That example, we are just changing the support conditions. Fixed one to hinge, hinge to right side, again hinge. Illustrative examples and some one gate questions. I think this is the basic things of your plastic analysis. If you want to know more about the plastic analysis, so you have to go deeper in the cases of plastic analysis. So because there is more questions, because there is more variables, variety type of questions like different type of geometry, continuous beam, and also UDL and prompt cantilever. These types of questions, these types of beams will come, and you have to find the plastic analysis, and you have to find the collapse load using plastic analysis. And please do not skip this portion, because you can expect minimum one question almost every year from your gate examination. So that's all. That's